Let's go ahead and take a look at problem 518. And there's a data file that you're given, PO 518. And I call this a QC problem, a quality control problem. And just to pull some bullet points out of the question itself, you have a quality inspector who is looking at random samples, batches of size 15 of parts coming off some assembly line. So at random, he or she selects 15 parts and then goes off somewhere and tests those 15 parts to determine how many of them are working and how many of them are defective. So each item that's selected has one of two outcomes. It's either defective or it's not defective. And we're told in the problem that there's a probability of defectiveness of 10%. So a defect probability of 10% for all the parts coming out of this line. So we can start to see how this may match up with a binomial experiment, especially when we think about the fact that each time the quality inspector selects a sample of size 15, it's independent of all other trials. So the next batch of 15 that's selected is independent from the first batch. So if those criteria are all met, then this would be an example of what's called a binomial experiment. And let's take a look at how we would use the binomial dist function in Excel to conduct some calculations on this scenario. The data set that you're given for the problem looks like this. It looks just like a probability distribution as we would have seen it in our previous block of material. We're given the possible values of number of defective items that can be found out of a batch of 15. We could get lucky and find that there are no defects at all out of 15. Or I could get 1 out of 15 or 2 out of 15 that are defective, all the way up to 15 out of 15 parts that are defective. So these are the only possible values. Clearly, it's a discrete variable. My lowest possible value is 0. My largest is 15. Now, we're given these probabilities in the data set, but if we look at the values, we may wonder where these numbers came from. And if we look at the cells themselves, we can see that these actually are results of this binomial dist formula. And in each case, we're saying equals binomial dist of that value of k, the number of defective parts out of a batch size of 15, comma, the number of trials, 15, the probability of success, 0.1 or 10%, and then the cumulative flag is set to 0. So here we're getting the probability of getting exactly 0 defects out of a batch size of 15 given a 10% defect rate. And we can see the same formula is copied all the way down. The only thing changing is the value of k. So here, for example, I have the probability of getting exactly 6 defective parts out of a batch of 15, given this 10% or a 0.1 defect rate. And this binomial dist formula will calculate exactly this number. We get 0.0019 out to 4 decimal places. So this, again, is an example of where the binomial dist formula was used to generate these probability values. And what I'd like to do is take a look at some different kinds of calculations we could do to ask and answer certain different kinds of questions. So I've added another tab to this spreadsheet here, and essentially the first column we've really just looked at. What I'm saying here is, okay, if k is my number of defective parts from 0 to 15, what's the probability of getting k for each of these k values? And I'll just replicate what was done in the original data set that we're given. So what's the probability of getting 0 defects? That's going to be, whoops, let me just raise something else to your attention. If I scroll up a bit, you can see where I've placed the number of trials at 15, the defect probability at 10%. And I've actually named these in this spreadsheet as N trials and def prob for defect probability. So I'm just going to refer to those cell locations to populate my binomial dist formula. All right, what's the probability of getting 0 defects out of 15, given that I have a 10% defect rate? Okay, now let's think about this conceptually a bit. If I'm getting a batch size of 15 and I have a 10% defect rate, kind of on average, I would expect somewhere around 1.5 of these parts to be defective. Of course, it's a discrete variable, so I can't get 1.5 for any given batch, but I'd expect on average to get somewhere in that realm. Okay, and we'll see that number becomes useful for us in the future. But that sort of gives us an idea as to where the center of the distribution may fall. All right, and we'll get a chance to look at this graphically in a moment. But let's start. Let's use our binom dist formula. Equals binom dist, binomdist, and Excel prompts us for the parameters. So first is the number I'm interested in, my k value. It's 0, comma, my number of trials, 15, comma, 10%, comma, 0, because I just want the probability exactly at k equals 0. Okay, so binom dist of k, comma, n, number of trials, comma, probability of success, comma, 0. And I'm going to copy this formula all the way down. And these numbers, again, should match up exactly with the numbers we were originally given. I think I have a few more decimal places displayed. Okay? But now, supposing instead of being asked what's the probability of getting k defects, I want to know the cumulative probability. I want to know the probability of getting k or fewer defects. And here I'm going to only modify the formula by turning that cumulative flag on. So I'll say equals binom dist of my same k value, comma, number of trials, comma, probability of success, comma, 1 this time. And that 1 tells the binom dist formula, hey, I don't just want the probability at 0, but I want the probability at 0 or anything less. Of course, in this case, 0 is the smallest value we have, but as we get to larger values of k, we'll see where this becomes important. I'm going to copy this formula down as well. And here you'll see that for k equals 0, the cumulative probability is exactly the same as the absolute probability because, as we said, 0 is the smallest value. But once we go up from 0 as our k value to a value of k equals 1, we see that the cumulative probability, the probability of being less than or equal to k, is the sum of the probability at k equals 1 and anything below it. So here I'm just accumulating the probabilities. If I get down, for example, to k equals 5, the cumulative probability is 0.9977503. That's the probability I've gotten by turning on my cumulative flag. So it should be the probability of getting 0 or 1 or 2 or 3 or 4 or 5. So I'm adding these probabilities together. And if we were to sum these first 5 values, and in my case, I'm going to look down here at my bottom part of my screen, down to my little summary bar at the bottom of my Excel window, and I see that the sum of these 6 probabilities here from 0 to 5 is exactly 0.9977503. So certainly it's giving us the cumulative probability, which is what we like. And I want to switch gears for a moment and just graphically show you what we've been talking about. What does this distribution look like? I've generated here in this little applet, if you will, a column chart that represents the probability distribution. This is the graphical picture of this probability distribution, and it's based on this binomial distribution calculation with n equals 15, probability of success equals 0.1 or 10%. And what I'm shading in red here is this for all the values of k from 0 up to 15. Okay, so the area of each of these rectangles is going to be the probability at each value of k. So for example, if I wanted to know the probability at 0, so I'm going to start at 0, end at 0. So now the red shaded bar is the bar that I've calculated, and it's pretty hard for you to see. The print is somewhat small, but the probability exactly at 0 is 0.2059, which is what our binomial dist formula gave us. If I wanted to know the probability, the cumulative probability from 0 up to 5, which is the one we just looked at, I can say 0 to 5. It's giving me these shaded areas. It turns out that after 5, the height of these columns gets so small that we can't see it on the scale anymore. But if we could, from 6 on, these would all be shaded blue. The red shaded areas are the ones I'm interested in, and the number we get, 0.9978. So to 4 decimal places, it's the same as the cumulative probability we've calculated here, 0.99775. Okay, so visually we can see what this distribution looks like. And where does this peak? Well, because the probability of success is at 10%, the distribution actually peaks somewhere around that 1.5 number that we came up with, right? Somewhere between 1 and 2, so where the peak would fall. Turns out our highest bin is the one that's right at 1. And that corresponds, if we look at our absolute probabilities, it's the largest probability value, 0.3432. All right, so just to get a bit of a visual picture of what we're calculating, I want to play with this just a little bit more because I think it's important to understand how we employ the information we have, the things we already know about probability distributions, in order to make further calculations about getting certain number or certain ranges of defects in this scenario. Supposing I wanted to know the probability of getting above a certain value of defects out of my batch size 15. What formula would I use? I want to know, in this case, let's say for k equals 0, I want to know the probability of getting more than k. So if k equals 0, I want to know the probability of getting 1 or 2 or 3 or 4 all the way up to 15. So anything, in this case, anything other than 0, because 0 is the smallest value. How would I find this using my binomial dist formula? Well, I know that the binomial dist formula gives me the probability at k, or the probability at or below k. In this case, I want to know the probability of being greater than k. Well, I know that my total probabilities must sum to 1. And we can see this by the fact that our cumulative probabilities increased all the way up to 1 and ended at 1. So if I want to know the probability of being greater than k, and all I have to calculate probabilities is this binomial dist formula that gives me probabilities at or below a certain value, well, I can use my complements rule and say the probability of being greater than k is going to be 1 minus the probability of being at k or below. So I'll start with the example of k equals 0, and I'll say, well, what's the probability of being greater than k? Well, it's going to be equal to 1 minus binomial dist of, and here's a key thing. I want to be careful about what is it that I'm subtracting in order to get the probability I'm interested in. So here I want to know the probability of being greater than k. So I don't want the probability at k to be included in my final result. So that needs to be included in the part that I'm subtracting. So the part that I'm subtracting here is going to be k and anything below. So I'm going to say 1 minus binomial dist of k, comma, n, comma, p, comma, 1. Right? And I get 0.7941. And you can verify that that's right. One interesting note is, in the case of 0, I could actually have said 1 minus binomial dist of 0, comma, n, comma, p, comma, 0, because I really want everything else, 1, 2, 3, 4, up to 15. But if I want a formula that's going to work for any value of k, then the right thing to do is to have this cumulative flag turned on, because if I said I want the probability of being greater than 5, well, then what I want to be subtracting is the probability of being 5 or less. So I would definitely want to have the cumulative flag turned on. Okay, just as a little point of comment. All right, so I have this formula that I can use for any value of k to find the probability of being greater than k. So give some thought just to make sure you understand why I'm saying 1 minus the binom dist, okay? And then importantly, what's in the binom dist? Why is it that I'm saying binom dist of k, comma n, comma p, comma 1, all right? And it has to do with the fact that I want the probability of being greater than k, and I'm going to contrast that to the probability of being greater than or equal to k. All right, and the difference here, of course, is that in this first case, probability of being greater than k, I don't want to include the probability of being at k in this result. Whereas in column E here, the probability of being greater than or equal to k, I do want the probability of k included in here, which means it cannot be in the part that I'm subtracting. Because I want the probability of being greater than k, and my binom dist only gives me probabilities less than k, I know I have to start with 1 minus something I can get from the binom dist. Okay? And I'll start this here, and we're going to see that I'm going to run into a little bit of a hiccup here. I can foresee that, but I want to start this so you can see where I'm going. So I'm going to say equals 1 minus binom dist of, okay? So anytime I want the probability of being greater than something or greater than or equal to, I have to use my complement rule and say 1 minus the piece that I can get, which is going to be out of the binom dist. All right? So here now, if I want the probability of being greater than or equal to k, then the probability of being at k cannot be included in the piece that I'm subtracting. So let's go back to the visual here. This may help us. Suppose I want the probability of being greater than or equal to 3. So I'm going to start at 3 and go up to 15. That's going to be my red shaded area, and presumably it continues all the way up here, but the values are so small we can't see it on the vertical scale. Well, the blue piece here is the part that I can get from the binom dist. I want the probability that's shaded in red, so I'm going to say 1 minus the piece I can get from my binom dist, all right? Well, what needs to be in the binom dist function? What's the part that I'm subtracting from 1? 1 is going to be that total probability from 0, 1, 2, 3, 4, 5, all the way up to 15. But I don't want all of those. I just want the values greater than or equal to 3. So what do I have to subtract from 1? Well, I have to subtract the probability of getting 2 or 1 or 0. Okay, that will leave me with the values 3, 4, 5, and higher. So when I implement this in Excel, I'm going to say 1 minus binom dist of 2, comma n, comma p, comma 0. 1 minus the probability of being at or below 2. That's for a value of 3. That's for being greater than or equal to a value of 3. So the piece that goes into this binom dist formula has to, in this case, not be k, but be k minus 1. This is where we say we have to be really careful now as we're implementing this. So if I want the probability of being greater than or equal to k, I have to remember that I cannot include the probability of k. I can't include the value of k in the portion that I'm subtracting. So I have to step down from k to k minus 1. And this obviously is going to be a problem for me when I'm trying to evaluate this for k equals 0. Because that would mean I'd have to put a value of minus 1 in the binom dist formula, and it does not like that. It'll give me an error. So binom dist the formula only works on values that are 0 or higher, non-negative numbers for k. So I'm going to have to skip 0 in this case and go down and start with my situation of being k equals 1 or above. Well, what do we know the answer has to be for k equals 0, by the way? The probability of being greater than or equal to 0, what's going to be 0 plus 1 plus 2 plus 3 all the way up to 15. And we know by definition that probability is going to have to equal 1. Okay, so that's the probability of being at 0 or above. We don't need the formula for that. And as a matter of fact, we can't use the formula for that. So let's step down to k equals 1 and find the probability of being greater than or equal to 1. And there we're going to be at 1 minus binomial dist of, and here now is where I have to say k minus 1. So I'm going to click on my k value, say minus 1, comma, n, comma, p, comma, 1. For these ranges of values, greater than, less than, greater than or equal to, etc., we always want to make sure we're using the cumulative flag turned on here. So we're always going to be using 1 as our last value. Okay, so now I have the probability of being greater than or equal to k. And if you, for good measure, you can compare this number to the probability we got for being greater than 0. And though it should make sense that those two numbers should be identical. So you can give that some thought. And then this formula we can copy all the way down. So now we've got the probability of being greater than k, probability of being greater than or equal to k. And, well, let's see, the one that I have not included here, let's go ahead and include probability of being less than k. All right, I think we got everything else except that one. So less than or equal to, we did greater than or equal to. What about the probability of being less than k? Once again, there are no values less than 0, so the probability of being less than k is by definition going to be 0. Okay, so what about the probability of being less than 1? I'll go ahead and put 0 in here. Probability of being less than 1. Well, there is a possibility of being less than 1, right? And that would be k equals 0. So when we calculate this, we should get the same value that we saw for the probability of 0. But to come up with a general formula we can use for finding the probability of being less than k, in this case, would I have to say 1 minus binomial dist, or can I just say binomial dist? Well, the key is to remember that binomial dist is always going to give me the probability at or below something. So if I want less than, then I don't need 1 minus. I can just say binomial dist of, and the question is, what do I put in here? Well, let's return to our visual. If I want to know the probability of being less than, let's say from 0 to suppose I want to know the probability of being less than 4. Well, what is less than 4? Is 4 less than 4? No, it's not. So if I specifically say less than 4, then I want to go from 0 up to and including 3. Now the red shaded area here. Okay? So therefore, the formula that I'm going to need to put in binomial dist is going to be a formula that would give me the probability of being at 3 or 2 or 1 or 0. So for being less than 4, I need to start at 4 minus 1. So that's going to be true in this case. I'm going to have to say equals binomial dist of k minus 1. So whatever my k value is, subtract 1 from it. And then again, I have n, comma, p, comma, 1. And as we saw, we should get, for the probability of being less than 1, exactly equal to the probability of being 0, because 0 is the only case that's less than 1. And then I can copy this formula down once again. All right, so we've exercised this binomial dist formula a handful of different ways, looking at using it to calculate the probability of being at a certain value, and then of being at or above, at or below, above, below, all the different ways you can play around with this formula. So again, note that you have to be careful, because in some cases you have to say 1 minus binomial dist. In some cases you have to say binomial dist of k minus 1. In some cases you don't put k minus 1, you put the actual value of k. So make sure you can keep track of where, what you have to use where. And I'll also try to post for you a little handout, a little one-page handout that kind of steps you through exactly what we've been working here. And just for reference, I've generated a column chart that shows you what these probabilities and cumulative probabilities look like for this distribution. In blue, I'm showing you the probabilities at 0, 1, 2, 3, 4, 5. And as we saw in the little applet, those numbers drop off very rapidly to zero once we get past 5 or so. There still are blue columns here. They're just, on this scale, they're just very, very small. But those numbers are not zero, okay? They're just very, very small numbers. In red, what I'm showing is the cumulative probability. Probability of being at or below each of these values of k. So at 0, the cumulative probability and the absolute probability are the same. But as we increase from there, we're adding the new probabilities to the previous probabilities. And again, it gets very close to 1, right around the same point where the probability is getting very close to 0, because the additional probabilities we're adding in are very, very small. So visually here you can see both the probability and the cumulative probability. And also, just to give you one more idea about how this function changes, how this distribution changes. This is in the case where the probability of success is 10%. Supposing we had a situation where that defect probability was 50%, which would not be a very good situation from a manufacturing standpoint. Okay. I changed this from 10% to 50%. It's going to update all my values, but take a look at what it does to the chart. Notice where the peak is in the probability distribution. It peaks right around the midpoint, so somewhere around 7.5 for n equals 15. And look at what happens to the cumulative probability. It starts out and remains very close to 0 for a while, and then it increases. Let's go up to 90% just to see what the opposite case would look like from our original case. We started out with a 10% defect probability. Let's see what a 90% defect probability looks like. It now looks like almost a mirror image, if you will, of the previous situation. Values stay at 0 for a long time, and then they slowly start to increase, and they peak at around 14 defects out of a batch size of 15. And of course, the cumulative probability stays very, very low for a long time, and then only rises rapidly to 0 at the end. So you can play around with this and get a sense for how different distributions might look. Remember, formally, if you were to change your number of trials to something larger, you'd have to increase these rows here, because you always want to include in your probability distribution everything up to that total number of trials. All right, well, we've spent a lot of time on this, but it's really important to make sure we understand how this function works. And we can see that it allows us to calculate some important probabilities that can be useful for us if we're in this kind of situation. It turns out there's a lot of situations that can be modeled using the binomial distribution. Defect probabilities here, they can be used to model customer satisfaction, things of that nature. So if we know the total sample size and the defect probability, or the probability of whatever we're looking for, satisfaction rates or things of that nature, this can be a very interesting function that can be used to model these things. Okay, supposing I wanted to know what value of k could I say, hey, I want to be 90% sure that I'm going to get at or below a certain number of defects. And again, this is really important for us. I mean, that sort of question I want to know about. I want to make sure my satisfaction rates are going to be at a certain number or higher, things of that nature. Those are very important questions to ask from a business perspective. So I can use my crit binom function if I want to know, what did I say, 90%? I want to be 90% sure that my numbers are going to be at or below a certain value. So we'll see how the crit binom function will help us there. So I'm going to say crit binom of, I'm going to plug in first my number of trials, then my probability of success, and then I'm going to plug in my trial cumulative probability value. Okay, and it's going to return to me the value 3. And what this is saying is, and again, if I look at my cumulative probabilities, are my probabilities of being less than or equal to k. So it's giving me that smallest smallest value of k for which the cumulative probability just exceeds the number that I put in. And as we can see, I put in 90%, so the first number I have that's just above 90% is 90. Well, it's 0.944 for the cumulative probability, and that corresponds to a k value of 3. So this can be a very useful function for us as well to establish what values of k meet certain criteria for cumulative probability, and we'll explore this further. Let's step back here for just a moment to our example we were looking at for this number of defective items in a sample of 15 products. There's a very different type of question, not very different, but there's a different type of question we might want to ask about these probabilities that we actually haven't covered here. And this is the example or the question about ranges of values. We talked about being at a certain value, above or below or less than or equal to, etc. But one that we haven't covered is ranges of values, and I thought it was worth taking a quick look at. Supposing I ask what's the probability of being between 2 and 6, having between 2 and 6 defects out of a batch of size 15. So I want to make sure I'm talking about the values of 2, 3, 4, 5, or 6. So let me add the word inclusive. So I want to make sure everyone's understanding what the question is. Supposing I want to know the probability of having between 2 and 6 defects out of a batch size of 15, given a 10% defect rate, and I want to make sure I'm including these values of 2 and 6. And visually, what do I want to know? I'm starting at 2 and I'm going up to and including 6. So these are going to be my red shaded areas, with the caveat that 6 is just a very small magnitude value. I just can't see it here, but it's also shaded red. How would I calculate that probability for this range of values? Well, if you think about what we were doing with our complements rule to calculate the probability of being greater than a certain value, we can apply that same approach here. Remember that the binomial dist function is going to give me the probability of being at a certain value or below, all the way down to 0. So if I want to find a range of values, in this case from 2 up to and including 6 as my values of k, I could use the binomial dist function to give me the with the cumulative flag turned on, to give me the probability of being at or below 6. This is going to be 6, 5, 4, all the way down to 0. But that's a little more than what I want. I want to stop at 2. So if I think then about, well, what do I need to subtract from the probability of being 6 or below in order to get the probability of being between 2 and 6 inclusive, then I can answer this question. I can just put together two binomial dist functions. And what I'll say is binomial dist of 6, comma, n, comma, p, comma, 1 in order to get 6 on everything below. And then I need to use another binomial dist to subtract away the parts that I don't want. Okay, so let's do that. So I'm going to say equals binomial dist of my larger value 6, comma, n, comma, p, comma, 1 minus, and here's where I have to be a little bit careful, minus what? You see, I don't want to say minus binomial dist of 2, comma, n, comma, p, comma, 1, because if I did that, I'd be subtracting away the probability of being 2 and everything below. So I have to be smart about it and say, no, I'm only going to subtract the probability of being at 1 and everything below. So in this second half of this binomial dist formula, I need to make sure I'm saying whatever the lower value is of my range minus 1. Again, comma, n, comma, p, comma, 1. And that should give me the probability of being between 2 and 6 inclusive. So 2, 3, 4, 5, or 6. All right. If I ask the same question, except now instead of saying inclusive, I said exclusive. I want to exclude 2 and 6. Here now I'm only interested in 3, 4, and 5. Well, I'm going to leave it to you to see if you can figure out how you'd modify this formula to get the probability of being between 2 and 6, exclusive of those two boundary values. Think about it just based on what we've done here, and think about what you'd need to do to get the probability of being between 2 and 6, exclusive. We're going to obviously use the same approach, but we're going to need to make a little modification to what we're including in these formulas. So what needs to be the k value, if you will, in the first binomial dysfunction, and then what do we want to be subtracting? The answer is it will certainly give us what should be a smaller number, because we're going to be not having including the probability of 2 and the probability of 6. See if you can get your head around how to find this value appropriately for the probability of being between 2 and 6, exclusive, and you can post a comment on the discussion board about that. So I'm going to just modify this here, and we'll leave it up to you to see if you can come up with a good way to approach this slight modification to the problem. Okay, thanks, and we'll get caught up on another block of material on the normal distribution very shortly. All right, so just to wrap up, we talked about distributions and summary statistics, and there's a shortcut to finding the summary statistics on a binomial distribution. If I wanted to know the mean and standard deviation for this binomial distribution, well, I could go back to my original probability distribution, and I could use sum product to find the expected value, right? The weighted sum of these values, where each one's going to be weighted by the probability. And then I could go on and find deviations and squared deviations, and then find the variance using the sum product again, just like we've done before. In this case, however, because of what we know about the math of the binomial distribution, it turns out there's some shortcuts that we can apply. So we can find the mean and standard deviation for this distribution. And we actually did part of this already. Remember I said, what's the most typical value we're going to find for the defect rates? And I said it's going to be where the distribution peaks, and it's around 1.5. If I've got a batch size of 15 and a 10% defect rate, then my expected value, my long-term average value, is going to be 1.5. Well, it turns out that that's actually correct. If I know n and I know p, in this case I'm just picking some different numbers. Suppose n is 10 or 2.5, whatever our 10 and 0.25. For any pair of n and p values that I have, we can calculate the probability, use the probability distributions and calculate the expected value and the standard deviation. Or we can use what we call a shortcut method, which works for binomial distributions. So for any n and p, the expected value of the distribution is going to be n times p. So 15 times 10% to give us 1.5. And the standard deviation can be found from this formula. If I know n and p, it turns out that the standard deviation will be the square root of n times p times 1 minus p. 1 minus p is going to be the probability of not having a success in generic terms, right? So if p is my defect probability, 1 minus p is the probability of having a working part, a defect-free part. Okay? So the standard deviation is always going to be n times p times 1 minus p, all square rooted. So that just about covers everything for the binomial distribution. And you can review this material and, again, play around with the data file I've posted and see how much you can replicate here. And that'll cover the material that we have for the binomial distribution.